Okay, lesson 2 is looking at gravitational fields and force. Should seem really similar to grade 11. I just want to be sure that everyone knows the difference between a field and a force. By the way, if you're curious as to what fields are, I put another YouTube video that isn't by me in the links. It really does help you visualize what a field is a little better. So, gravity in a nutshell. Gravity is an attractive force between any two objects with mass. Newton originally described it as a force of attraction. We now think of it more as a bend in space-time, an Einstein model, but we can actually still describe the effects using the forces and the model that Newton created. It's not accurate in what it really is, but the calculations are still extremely accurate. At most scales, we can still use Newton's law to predict forces, and unless you're dealing with cosmology or dealing with things at the quantum level, really it's all you're ever really going to need is to describe it as a force using Newton's model. So, what is a model? Well, scientific modeling is an activity to make a part of the universe easier to understand, quantify, visualize, or simulate. Now, it basically is representing an empirical object in a logical and objective way. But the important thing to remember, especially when we deal with forces and fields of field theory, is it's what we call simulacra. Means it's simplified reflection of reality, but it's useful, but it's not real, if that makes sense. It's a way to calculate the attraction between two objects using a field, using forces, but that's not really what's happening. There's no force. Even Newton himself said this idea that there's this miraculous invisible force pulling these two things together is ridiculous. My theory just basically explains what the magnitude and direction of the force would be between two objects. I don't really understand what's causing it. And it wasn't until Einstein at the beginning of the last century that we started getting an idea. And we're still not sure general relativity is the right solution to what's actually making them go together. The good thing is, 99% of the time, we just care what the force is. We don't care what's actually causing it. So this model, using Newton's laws, is useful enough. It lets us calculate and describe reality even if we don't understand the cause of it. All right? So, field theory is, again, it's a mathematical model to describe forces. There are no field lines really in space. So it's a mathematical quantity. So a field is a physical quantity that has a value for each point in space. So it's a description of what the force would be at some point in space due to an object, either the charge or the gravity or the magnetic field. So for example, we use a weather forecast, right? We describe the wind velocity as a vector, and each vector represents the speed and direction of air at that time. And then we say, okay, this is what we think that is going to cause. Think it's the same with gravity. A field of force is described what the force would be if there were an object there. You've actually already seen the gravitational field. You just don't know it yet. In fact, it's that little g that we used for mg to find your weight. So if we model gravity as a field of force that radiates out from an object, everything near that object would be attracted to it. The closer it is, the bigger the attraction will be. So we can basically describe the Earth as sort of a field like this, where these lines are basically what the vector would be if we put an object there. Remember, there's no object there. This doesn't really exist. It's a mathematical model, okay? These vectors basically describe what would an object be. And if we put a unit mass there, so basically something with a mass of 1, and find the force, well, we know the force is gmm over r squared. If the little object just had a mass of 1, it would vanish, all right, because it would just be times 1, and you would get this. And this is actually what that little g in force of gravity equals mg is, and why we can only use it on the surface of Earth for Earth. Because g is only 9.81 if you plug in the mass of Earth and the radius of Earth as your distance. You get a value of 9.81. That's where that number comes from. If you're not on Earth, or if you're not on the surface of Earth, that G, that field strength, is actually different. So what G actually is, the gravitational constant we gave you, is it is the gravitational field strength on the surface of Earth due to Earth. So it's what the force would be on a 1 kilogram mass if you basically placed it on the surface of the Earth. And you might say, well, why is that useful? Well, then we can use it to find the force on any object by just multiplying. So if I know what my acceleration is, remember that's also your gravitational acceleration, now we can find the acceleration of any object at any distance just using that gravitational field. We can find the force by just multiplying that gravitational field by the mass of the object. So that's actually what the force is, right? So the gravitational force is the gravitational field times the mass of the object. It is actually just still this equation. There's no difference between this equation and this equation. It's just G is actually this. It's not always 9.81. 9.81 is just the solution to that on the surface of Earth. The other thing to keep in mind is that's the attraction of both objects. You're pulling on Earth as much as Earth is pulling on you. The only difference is you're way lighter than Earth, so Earth doesn't move noticeably, but you do. It actually does. It moves a tiny, tiny amount when you jump. The Earth jumps up to meet you, but so tiny that like it's less than the width of a hydrogen atom, so we don't notice it. How do we use it? Well, let's say we want to find the gravitational field at an altitude of 500 kilometers. You're in a low Earth orbit on a spaceship, and you want to know what the force of gravity is on you. And this is actually kind of neat because we usually think you're weightless. You're not weightless. You're in microgravity because you're falling, but you're actually falling at a different rate. But how would we find what the force of gravity actually is on you that's holding you to the Earth to keep you in that orbit? Well, the most important thing to remember is putting the numbers in right. The radius is the distance from the center of Earth to the object, from the center of the object. So for the Earth doesn't have a radius of 0, so you actually have to add the radius of Earth to the altitude before you start, and then convert it to meters, because to get newtons we need meters. By the way, this is the biggest mistake people make on these questions, is they either forget to add the radius of Earth, or they forget to turn it from kilometers to meters. If you get that right, the rest of it's just plugging in. So, the acceleration is g times the mass of Earth divided by the radius. So, g is the gravitational constant of the universe, always 6.67 times 10 to the minus 11, times the mass of Earth, which we look up, divided by that radius, squared. Don't forget to square it. That's the second biggest mistake people will make on this question, is forgetting to square that number. And we get a g of 8.5. So when you're 500 kilometers above the Earth, the gravitational field has actually shrunk from 9.81 to 8.5. It's actually still, most of it's still there. So what would your weight be? What would the force of gravity be? Well, then we can just find your weight using mg. But we plug this number in for the g, and we get 720 newtons. So the gravitational field strength dropped from 9.81 to 8.5. Your weight would drop from about 850 to 720 newtons. So why is this useful? Well, if we find the field, then I don't need to use that giant equation for every astronaut. I just multiply that field strength by the astronaut, by the ship, by whatever I have in space. So it's a lot easier to find the forces. All right, so that's this lesson. I hope you have no problems getting the worksheet done. See you next time.